In this lesson, we're going to extend the concepts of systems of equations where we solve with which we solve with two variables to systems of equations that are going to have three variables. Now, if we have a situation like this, where we now have an added z component, there's still going to be an infinite number of what we refer to now as ordered triples. So solutions of equations with three variables can now be pictured on this three-dimensional coordinate plane where you now have a new axis. We're not going to be graphing these, but I do want you to see that each of these equations are going to form what we refer to as a plane. And so we're now going to want the x, y, and z components that are going to make the equation true. So if we just look at a few solutions to this, we could see that we could let any one of the variables equal 6, while the other two are 0. And that would give me 6 plus 0 plus 0 is 6. And notice we could do that regardless of which variable we choose. But we could also come up with 1, 2, and 3 in any particular order, or 4, 1, and 1 in any particular order. So all of these are going to be solutions to this equation. Now, when graphing a linear equation with two variables, remember how we got a line. But now if we were to graph this equation with the third variable, we would get one of these planes. And so graphically, the solution to a system of equations with three variables is going to be a location where all three planes cross. And you could think about these like walls and floors of a building where they all intersect at a corner. So let's take a look at how we can determine how many solutions a system with three variables can have and what that would look like. So if we were to have one solution, that would mean, as we mentioned before, if the red plane was a floor of a building and the blue and green planes were walls, then these would all intersect at one location, which is the corner of that room. And we could also have 0 points of intersection, but that could occur in numerous ways. It could occur to where all the planes are parallel to each other, similar to just floors of a building that would never intersect. It's possible that two of them are parallel and one of them intersects. Again, the point of intersection between the green and blue would be there would be an infinite amount of them anywhere that lies along this line. And same thing with the green and the red, but there's no single point of intersection between all three planes. The last situation could be to where we have all three planes intersect each other's as pairs, but not as one single location. So each of these situations would have no solution. Now, just like if the planes were, or if the lines were the same line in two variable systems, we could also have a situation where we have infinite solutions. This could be similar to a binding of a book where all the pages are bound together, all of those planes are bound together right at the binding of the book. And notice that there's an infinite amount of points of intersection between the green, blue, and red planes. They all form a line. Now, if you take a look here, the three planes form the same plane, and this would also be an infinite number of solutions. Now, we're not going to be graphing any of these, but it is helpful to see what these solutions are going to be when we end up getting these different situations. So now let's take a look at an example here. Now don't get too scared with this. This is just a third variable, which now means that we have a third equation. Now it turns out that we're going to be solving this using the elimination method in a very similar way to what we did with two variables. With two variables, we just listed, with two variables, we ended up multiplying by some particular number that was going to get opposites. Here, we're going to eliminate the same variable from the first two equations, and then again from the second two equations. And the purpose of this is to get it down to a two-variable system. So why don't we start off by multiplying the second equation here by 2 so that I get opposites for the y's. Now notice I have to multiply every term by 2, which is how we got this second equation. And now if we were to combine these terms together, y's cancel out, and we're left with 7x plus 10z equals 19. And just like that, we've reduced it down to two variables. Why don't we do the same thing with the second two equations? If we list 2x minus y plus 3z equals 4, along with the last equation, we want to eliminate y again. So we look over to the y's and determine what we need to multiply by in order to get opposites. Since we already see a negative 3y here, it would be nice to see a positive 3y here, which is why we're going to multiply by negative 3. And if we distribute that negative 3 through, notice how the y's are again opposites, which now cancel out. And when we add those two equations together, we get negative x minus 4z equals negative 13. And notice at this point that we have two equations with two variables. So if we line those up, we can solve with elimination again. So now let's multiply the bottom equation by 7 in order to get opposites for the x's. When we do so, that gives us 7x and negative 7x, which will cancel. And therefore, when we add these equations together, we get negative 18z on the left, and we get negative 72 on the right. Dividing by negative 18 gives me that z is equal to 4. Well, if z is equal to 4, we can plug that into any one of these two equations here in order to solve for the x variable. So let's plug it into the bottom equation. We plug in 4 for z, and we now solve. This is now negative 16, so if we add 16 to the other side, we get 3. So if negative x equals 3, then x equals negative 3. We now have two variables, which is the solution to this system of equations with only two variables. But don't forget, in the original equation, we had 3. So we can now take the x and z components and plug those in to one of the original equations. I've chosen to plug it into the second equation because it looks like all the coefficients are the smallest. So here we have 2 times the x value of negative 3 minus y plus 3 times the z value of 4 is equal to 4. And if we simplify that and move everything around, then we end up getting that y is equal to 2. In order to see that, negative 6 plus 12 is 6. So if I subtract 6 from 4, I get negative 2. Negative y is negative 2, so y equals 2. And therefore, with a third variable, our solution to the system of equations is negative 3, 2, and 4. So the way that we solve systems of equations, although we're not going to ever have to worry about the graphical representations, we do want to recognize that we're solving using the elimination method, just like with two variables.